it is not advisable to operate a Wye-Wye transformer with a delta system lacking a neutral connection. Understanding the configuration of both the transformer and the supply system is crucial. A Wye-Wye transformer features both its primary and secondary windings arranged in a Y configuration. This configuration inherently includes a neutral point, which ideally should be connected to the system's neutral to establish a stable ground reference. In contrast, a delta system does not inherently possess a neutral point. Consequently, there is no direct reference to ground potential within the delta configuration itself. When a Wye-Wye transformer is improperly connected to a delta system devoid of a neutral, the neutral point of the transformer's winding experiences a phenomenon known as floating. This floating neutral implies that the voltage difference between the neutral point and the actual ground potential fluctuates erratically, influenced by the varying load demands placed upon the transformer. Such voltage instability can precipitate a cascade of problems for equipment connected to the transformer. Overvoltage and undervoltage conditions can arise, jeopardizing the proper functioning and longevity of sensitive electronic devices and machinery. The absence of a neutral connection in a delta system can also exacerbate issues related to stray or transient voltages. These unwanted voltages, often originating from external sources or internal circuit anomalies, can exploit the transformer winding as an unintended pathway to ground. This detour can manifest as ground faults, causing protective devices to trip and potentially damaging equipment. The implications of ground faults extend beyond immediate equipment damage. They pose significant safety hazards, increasing the risk of electrical shocks and creating fire ignition sources. Therefore, adhering to proper grounding practices and avoiding configurations that leave the neutral point floating is paramount to ensuring electrical system safety and reliability. Examining the potential sources and mitigation strategies for stray voltage is important. Stray voltage, also known as transient voltage, can arise from various factors. Firstly, inductive coupling between conductors can induce unwanted voltages in nearby circuits. Secondly, capacitive coupling, especially in systems with long cable runs, can contribute to voltage leakage. Thirdly, grounding issues, such as inadequate grounding or ground loops, can create voltage differentials that manifest as stray voltage. To mitigate stray voltage, several strategies can be employed. Firstly, proper shielding of cables can reduce inductive and capacitive coupling. Secondly, implementing a robust grounding system with low impedance paths to ground can minimize voltage differentials. Thirdly, using filters and surge suppressors can dampen transient voltage spikes. When dealing with power systems, it is also helpful to consider grounding systems. There are several grounding systems commonly employed in electrical installations, each with its own advantages and disadvantages. Firstly, the solidly grounded system provides a direct connection between the neutral point of the transformer and ground. This system offers excellent ground fault protection, but can result in high fault currents. Secondly, the impedance grounded system introduces an impedance, such as a resistor or reactor, between the neutral point and ground. This system limits fault currents but provides less sensitive ground fault detection. Thirdly, the ungrounded system, also known as the floating system, does not provide a direct connection to ground. This system offers high service continuity but can experience overvoltage conditions during ground faults. When selecting a grounding system, factors such as fault current levels, protection sensitivity, and service continuity requirements must be carefully considered. Regarding the transformer configuration, several configurations exist beyond the Wye-Wye. Firstly, the delta-delta configuration features both primary and secondary windings connected in a delta arrangement. This configuration is suitable for applications where a neutral point is not required. Secondly, the delta-Y configuration has a delta-connected primary winding and a Y-connected secondary winding. This configuration provides a neutral point on the secondary side and is commonly used for step-down applications. Thirdly, the Y-delta configuration features a Y-connected primary winding and a delta-connected secondary winding. This configuration is less common but can be used for specific applications such as power factor correction. Selecting the appropriate transformer configuration depends on the specific voltage transformation requirements and the availability of a neutral point in the system. Let's explore the potential consequences of operating a Wye-Wye transformer without a neutral connection in greater detail. Firstly, the floating neutral phenomenon introduces significant voltage imbalances across the phases. This imbalance can lead to uneven loading of the transformer windings, potentially causing overheating and premature failure. Secondly, the voltage fluctuations caused by the floating neutral can disrupt the operation of sensitive electronic equipment. Programmable logic controllers, variable frequency drives, and other microprocessor-based devices are particularly susceptible to voltage variations, potentially resulting in data corruption, equipment malfunction, or even permanent damage. Thirdly, the lack of a neutral connection can impede the proper functioning of ground fault protection devices. Ground fault circuit interrupters and ground fault relays rely on a stable neutral reference to detect ground faults effectively. Without a neutral connection, these devices may fail to operate correctly, leaving personnel and equipment at risk. Furthermore, the presence of stray voltage can introduce noise into sensitive electronic circuits, interfering with communication signals and disrupting data transmission. This noise can manifest as errors in data acquisition systems, communication failures in control networks, and performance degradation in audio and video equipment. The mitigation of these problems involves the implementation of a properly grounded neutral connection. This connection provides a stable reference point for voltage regulation, facilitates the detection of ground faults, and minimizes the effects of stray voltage. The installation of a neutral conductor should adhere to the requirements of the National Electrical Code, specifically Article 250. This article provides detailed guidelines for grounding and bonding electrical systems to ensure safety and performance. When troubleshooting electrical problems in systems with Wye-Wye transformers, several diagnostic techniques can be employed. Firstly, voltage measurement should be taken at the transformer terminals and at various points throughout the connected circuits. These measurements can reveal voltage imbalances, voltage drops, and the presence of stray voltage. Secondly, current measurements can be used to assess the loading of each phase and identify potential overloading conditions. Thirdly, insulation resistance testing can be performed to detect insulation breakdown in the transformer windings and connected cables. Fourthly, ground impedance testing can verify the effectiveness of the grounding system and identify potential ground faults. By systematically applying these diagnostic techniques, electrical problems can be effectively identified and resolved. When considering the impact of harmonics on power systems, it is helpful to understand their origin and effects. Harmonics are non-sinusoidal waveforms that are integer multiples of the fundamental frequency. These waveforms are typically generated by nonlinear loads such as variable frequency drives, electronic ballasts, and switch-mode power supplies. Harmonics can cause a variety of problems in power systems, including increased current flow in neutral conductors, overheating of transformers and conductors, voltage distortion, and interference with communication equipment. To mitigate the effects of harmonics, several techniques can be employed. Firstly, harmonic filters can be installed to block harmonic currents from propagating through the system. Secondly, using harmonic mitigating transformers can reduce the generation of harmonics. Thirdly, specifying equipment with low harmonic distortion characteristics can minimize the contribution of individual loads to the overall harmonic content. In addition to addressing harmonic issues, power factor correction is also important for optimizing power system performance. Power factor is the ratio of real power to apparent power and represents the efficiency with which electrical power is used. Low power factor can result in increased current flow, voltage drops, and higher energy costs. Power factor correction involves adding capacitors to the system to compensate for the inductive reactance of loads. This compensation improves the power factor, reduces current flow, and increases the efficiency of the power system. When installing and maintaining electrical systems, safety is of paramount importance. Adhering to lockout-tagout procedures is essential to prevent accidental energization of equipment during maintenance or repair. Lockout-tagout involves disconnecting the equipment from its power source, applying a lock to the disconnect switch, and attaching a tag indicating that the equipment is out of service. This procedure ensures that the equipment cannot be inadvertently energized while work is being performed. Furthermore, wearing appropriate personal protective equipment is crucial for protecting against electrical hazards. This equipment includes insulated gloves, safety glasses, and arc flash-rated clothing. These items provide a barrier between the worker and potential electrical hazards, reducing the risk of injury. Regular inspection and maintenance of electrical equipment is also essential for preventing failures and ensuring safety. This includes inspecting cables for damage, tightening connections to prevent overheating, and testing protective devices to verify their functionality. By following these safety practices, the risk of electrical accidents can be significantly reduced. In the context of dairy facilities, stray voltage can pose a particular challenge. Dairy cows are highly sensitive to stray voltage, and even small voltage levels can cause stress, reduce milk production, and health problems. Stray voltage in dairy facilities can originate from a variety of sources, including faulty wiring, improper grounding, and nearby power lines. To mitigate stray voltage in dairy facilities, several measures can be taken. Firstly, a comprehensive grounding system should be installed to provide a low-impedance path to ground. Secondly, equipotential planes can be created in areas where cows are present to minimize voltage gradients. Thirdly, isolating transformers can be used to isolate sensitive equipment from the main power system. Regular testing for stray voltage is also essential to identify and address any potential problems. Furthermore, collaboration with electrical contractors and agricultural experts can help to develop and implement effective stray voltage mitigation strategies. When considering the specific parameters mentioned, the primary voltage is 12,470 volts with the grounded Y configuration, and also at 7,200 volts with the grounded Y configuration and 4,160 volts. While the secondary voltage is 480/277 volts. This information is important for understanding the voltage transformation ratio and the grounding requirements of the system. The fact that the dairy facility has been operating for 15 months with stray voltage problems suggests that the grounding system may be inadequate or that there are other underlying issues that need to be addressed. A thorough investigation of the grounding system, wiring, and equipment is necessary to identify the root cause of the stray voltage problems. Implementing the appropriate mitigation strategies can help to improve the health and productivity of the dairy cows and ensure the safe and reliable operation of the electrical system. It is important to consult with qualified electrical professionals to ensure that the grounding system is properly designed and installed and that all electrical work complies with the National Electrical Code and other applicable standards. This will help to prevent future stray voltage problems and ensure the long-term safety and reliability of the electrical system. When examining the implications of using a delta system to supply a Wye-Wye transformer, it's crucial to understand the fundamental principles governing voltage and current relationships in both configurations. A delta system inherently lacks a neutral point, which is a designated reference point at ground potential. In contrast, a Wye-Wye transformer necessitates a neutral connection to establish a stable voltage reference and facilitate balanced current flow. When a Wye-Wye transformer is directly connected to a delta system without a neutral, the neutral point of the transformer's windings becomes effectively isolated or floating. This floating neutral introduces several critical issues. Firstly, the voltage distribution across the transformer's phases becomes unpredictable and susceptible to imbalances. Uneven loading or variations in source impedance can cause significant voltage differences between phases, potentially leading to equipment malfunction or failure. Secondly, the absence of a neutral connection impairs the ability of ground fault protection devices to operate correctly. Ground fault circuit interrupters and ground fault relays rely on a stable neutral reference to detect and respond to ground faults. Without this reference, these devices may fail to trip, leaving personnel and equipment vulnerable to electrical hazards. Thirdly, the floating neutral can exacerbate the effects of harmonic currents. Harmonic currents, which are multiples of the fundamental frequency, can circulate through the transformer windings, causing overheating, voltage distortion, and interference with sensitive electronic equipment. The absence of a neutral connection prevents these harmonic currents from being effectively shunted to ground, compounding their detrimental effects. In summary, operating a Wye-Wye transformer from a delta system without a neutral is generally not recommended due to the potential for voltage imbalances, impaired ground fault protection, and exacerbated harmonic distortion. Proper grounding practices, including the establishment of a neutral connection, are essential for ensuring the safe and reliable operation of electrical systems.